Log on, tune in, find out. Another good idea from Cambridge.
The talk this morning is from Guido Vitale, and yet more variety on our. We're having a variety of inverse problems this morning. So, inverse problem on microscopy. So, Guido, take it away.
Okay. Now, first, thank you to the organizer for accepting my talk, and thank you to Newton Institute to refund my lodge expense. Then I'm going to talk about force traction microscopy. Force traction microscopy is an inversion method that allows to obtain, to reconstruct a force field exerting on an elastic medium by the knowledge of the displacement of the elastic medium and the material property of the elastic medium itself. The reconstruction of force field exerted by living cells in their surrounding environment is a quite popular issue in biophysics. Usually biophysicists prepare in laboratory an elastic material, which they call matrigel, seeded with several beads. So when a living cell is embedded in such a material, he exerts some force, and one can observe the displacement of such beads. By the knowledge of the displacement of such beads and by the knowledge of the material properties of matrigel, one can reconstruct the actual traction pattern of the cell by means of an inverse problem, basically. In 1999, Dembo and Wang solves such a problem in the simple situation on which a cell is lying on a flat substrate. Then in 2010, Ligand and Chen solves such a problem when a living cell is fully embedded in a three-dimensional matrigel box. Their approach includes the use of the green function of elasticity, which can be found exactly on books in the flat case, and it should be approximated by finite elements in the full three-dimensional case with an expensive algorithm. So the use of green function of elasticity allows to write this integral equation, and this integral equation has to be inverted after involving a regularization, since this inversion is, as you know, ill-posed. Now in 2006, my boss, is Davide Ambrosi, proposed to solve the same problem of Michael Dembo, so the cell lying on a flat substrate, by borrowing techniques from optimal control, and he actually solves this problem in a simplified average setting. Such a method, the optimal control method, is can treat arbitrary complex geometries. Then it can be generalized easily to more complex material behavior. It can be also easily generalized formally to the case of nonlinear elasticity, and can be implemented straightforwardly using finite element existing code. So now I want to show you a movie. Okay, perfect. So in this movie you can see a cell which is wandering in its natural environment, which is a actual three-dimensional environment, and the pattern of the force applied by the cells are really three-dimensional. So as you can see, for biologists it's very attractive to can reconstruct in laboratory an actual three-dimensional pattern of force field. Then what I have done during my PhD is to extend the optimal control approach in a full three-dimensional environment. So in this talk I will derive formally the equations, then I will state the posedness of the problem, and then I will show you some numerical results. First of all, we stick with such a setting with the domain omega is a domain filled by an elastic material. The internal boundary, say gamma n, is the boundary where the cell traction applies, so it's a Neumann-like boundary condition. The external boundary, gamma d, is the boundary where homogeneous Dirichlet condition applies. Those points x1, x2, xn are the fluorescent beads that one observe in laboratory, and actually in those points measurements are available. So biologists measure displacement, I call U01, U02, etc. So when one wants to solve an optimal control problem, what it usually does is to introduce a penalty function which combines the discrepancy between measured data, which I call U0, and calculated displacement, and then it regularizes such a function with a Tikhonov, for example. We use Tikhonov penalization. This function is constrained to a PDE. The PDE relates the force field exerted by the cell to displacement of the gel in the box, and this is the PDE of linear elasticity. Also, we have a constraint because cells can exert only force that are balanced, so they are we have the constraint of null average force and null average momentum. As I've said, C, capital C, is the UK elasticity symmetric positive fourth order tensor. Then epsilon is the Tikhonov filter. O is the observation operator. So since we want to observe displacement at some points, the observation operator starts to be a list of Dirac delta centered in such points. And then U0, as I said before, is the list of given displacement at such experimental points. So this is very trivial. Introducing an adjoint field, one can write the previous minimization problem as a set of coupled partial differential equations. So as we can see, we have the forward problem of elasticity, the adjoint problem, whose forcing term is the discrepancy between measured and calculated displacement, and those two PDEs are coupled on the Neumann boundary where cell traction applies, and note that cell traction is proportional to the adjoint field. For the moment we are neglecting constraint, but we can see that in a moment. So as you can see, it's a couple of elliptical PDE, and they are really implementable. So I rewrite this system in variational form, and for this system I can state our posedness results. In particular, I have found that the displacement belongs to H2, and the adjoint fields belong to W1S with S closer to 1, and the trace of the adjoint field belongs to H1/2 of the boundary. Also in this set of PDE I've incorporated constraint of null average force and null average momentum in an easy way, because such a subspace of force having null average force and momentum is a closed subspace of H2. The techniques I have used are more or less well known. I have used standard techniques for find minimum for convex and coercive functional, since our penalty functional is convex and coercive. And then I've used result for the elasticity equation. Also, I've used the result for the elasticity equation when Borel measure like Dirac delta are involved, and then I can prove also regularity result for the adjoint field at the boundary. So to link this procedure to inverse problem, is quite easy. We have to define the best approximation solution in the usual way. Then I found that the operator which links measure displacement with forces has closed range. It is easy because its range is finite dimension, and then I can apply some known theorem as I can see, as we can see, best approximation solution exists and depends continuously on the data, and then the solution of the regularized problem tends to the best approximation solution as epsilon, the Tikhonov filter, tends to 0, and the same holds if the data are noisy. So now let's turn to numerical results. We have done some simple validation tests to verify the reliability of our method. First, we set a given force field, and we evaluate the displacement solving numerically the forward problem of elasticity. So we give a force, and then we calculate displacement that such a force gives. Then we observe the displacement in some point, in some given point, and then we take this measure as a data for our inverse machinery. Then we solve our machinery, and then we evaluate the error, the discrepancy between calculated and given a priori force. So our numerical setup is similar to what I've shown you before. This setup is quite similar to the one you can find in a biophysical laboratory. We have our box filled of elastic material, and then we have the hole. The hole represents the cells. And also we choose to work with dimensional quantities, as you can see, to fit the needs of biophysicists. Before going on, let me just note that our approach, our variational approach, costs as the number of degrees of freedom of the grid, while the green function approach costs more than ours. Okay, so I give a traction. Our traction is a dipole-like traction that is quite similar to what can be exerted by a living cell, and these are the displacement that such a force gives. Then we perturb also such a given data with some noise. The amplitude of this noise is what can be found in the practical application, and the probability function we have chosen is a uniform one, but just for simplicity, because it's simpler to implement on a code. Then numerical results. Numerical results are quite similar to what one can be found in literature when dealing with such problems. In particular, these plots refers to the error on this measure between measured and calculated displacement, and error between given and calculated reconstructed force as a function of the regularization parameter epsilon. On the bottom we have the L curve and its curvature. What we can see is that error on the force field are more or less of 40%, and what also we have observed is that the epsilon at the corner of the L curve is very close to the epsilon that minimizes the discrepancy between calculated and given force, fortunately. Then there are some here. It is a plot. There is a plot of our reconstructed force. As we can see, despite of the fact that the error is about 40%, the pattern of the force field is quite well reconstructed. Also, we know that error concentrates where the values of force are greater. Now some sensitivity analysis for our machinery. We have varied the number of beads. As you can see, increasing too much the number of beads do not decrease so much the error of reconstruction. While if I take the beads far away from the boundary where force applies, errors grows very fast. Also, we have tested our machinery on in a case when the border with the internal border is not so trivial. We have perturbed our ellipsoid with some bumps, and what we can observe is that obviously error of reconstruction increases, but also increases the optimal value of epsilon. Also, we have refined our grid, and what it can be found is that a convergence grid maybe exist, but obviously when refining a grid we increase the number of degrees of freedom, and then since the information we have is the same, errors seems to grow a bit. So to resume, numerical simulation yield reconstruction error about 30–40%, but good agreement between the pattern of given force. Also, we have found that in this case the L curve criterion works well, and then we have found a strong dependence on beads distance and a weak dependence on beads number after a minimum number is given. So to conclude, we have proved well posedness for the problem of interest. Then we have write down a FEM code using a free FEM and using TechGen as a mesh software, and then we have done some numerical tests of reliability. And what we ought to do is to test our machinery on a really experimental situation. So we have to mesh up actual shapes of cells that are very complex. We have to use your tool obviously with real biological data, and also we hope to extend our approach to more complex material behavior. So thanks for your attention.
Do you have any questions for Guido? Come on, get your juices flowing. Right, well, I couldn't quite follow one of the things at the beginning, and I was wondering, the force field that you're trying to retrieve, I'm right in thinking it's a sum of delta functions?
Well,
continuous?
Force field is, we have found well posedness for a force field in H2 of the boundary. It's not, it cannot be a delta function for for theoretical purpose. We cannot reconstruct we cannot reconstruct a delta function like force field. Okay. In fact, force field is the trace of the adjoint state, and we cannot reconstruct things that are measures. But
so it's not that you're trying to identify points where the force is coming from.
No, what I'm trying to identify is the force field at the boundary. Is a field that lives on. Okay, is a force field that lives here. Delta function are in the observation operator.
Right.
So I are inside this term because I evaluate the displacement field on the experimental beads, and I look at the discrepancy between measured data here in the beads and the calculated one here. But obviously, it's of it can be of interest to reconstruct a force field which is a measure. That's because biologists say that force traction concentrates in some points. They are called focal adhesion sites. So cells adhere on substrate on these focal adhesion sites that are very small. And so if one can do some mathematics to justify the presence of a measured term here, it will be of very interest, because it allows to identify the focal adhesion sites. But this is not the case of my work, unfortunately. Thank you.
Any other?
I think it was a very nice model. It's a linear model, and when you're observing the cell moving, it seems to have quite large deformations for its size. Do you have concerns about your model being linear, and
Okay.
perhaps could develop a non-linear elasticity model for it? What difference does that bring to this force estimate?
Okay, two things. The movie does not concern the real experimental setup, but it's only a movie just to show you how cell behaves. But experimental setup is quite different. Secondly, what we ought to do is clearly generalize the approach to nonlinear elasticity. This can be done at least formally, not from the point of view of well-posedness. This is, I think, too hard for me. But this is formally possible to generalize this approach. It's just a matter of here write down the full nonlinear elasticity equation, and instead of this linear adjoint problem, substitute this linear adjoint problem with let me say the adjoint of the differential of the nonlinear elasticity operator. So it can be done. I've done it writing on the paper, but I write down it on a sheet, but I'm not able for the moment to implement. It's just a matter of doing calculation and then to doing some programming.
Do we have any further remarks or questions? Okay then, so let's thank Guido once again for